Ah, got it.
Yeah, so hi everyone, welcome to the CNSE module seminar. Today we are very happy to have Bruno Mera from University of Lisbon to talk about the uniqueness of Landau levels and the analogs in Python networks. Yeah,
so hello everyone. It is truly an honor to be here. I want to thank you for coming and thank you, G, for supporting my visit and everything. I'd like to also thank Ashwin Vishwana for supporting, for making this visit possible. So I'll be here for a month in case anybody wants to discuss, but I think this is important information. So today I will be talking about uniqueness of Landau levels and their analogs with higher Chern numbers. So this is joint work with the Tomoki Ozawa from the Advanced Institute for Materials Research at Tohoku University in Japan. I did this work in my previous position where I was also at the IMR at Tohoku University. Now I'm currently at Instituto Telecomunicações and Instituto Superior Tecnico in Lisbon. Okay, so let us start. So this is the outline of my talk. I will begin by giving perhaps my personal view on the concept of Bloch bands and quantum geometry. Then I will speak about this concept of Kähler bands, which we introduced recently, and it has found, well, they occur naturally and has found interest in quantum method, namely in fractional Chern, in the context of fractional Chern insulators, and also in twisted bilayer graphene. And then I will specify to a particular case of Kähler bands, which is that of ideal Kähler bands or ideal bands, as G introduced, and we also call them ideal flat bands, and then after that I will go to an even more particular case, which is that of truly flat Kähler bands. So we will see all these three. Well, we'll start with the most general setting of Bloch bands, then we will go to Kähler bands, ideal Kähler bands, and then flat Kähler bands. And these ones, the last ones, are unique in some way. I will make precise. Okay. So Bloch bands and quantum geometry. So we want to abstract the concept of the Bloch wave function, and so I will consider the real space lattice Z2. So I'm working in two spatial dimensions, a full rank lattice in Euclidean space R2, and then Z2 is also dualizing, is also the reciprocal or dual momentum space lattice. Okay, so definition. Bloch wave function. A Bloch wave function in two dimensions is determined by a family of non-vanishing vectors, U sub k, in a fixed Hilbert space, H, which is smoothly parametrized by k in R2. And here R2 will be the universal cover of the Brillouin zone. Okay, and it satisfies the following quasi-periodicity condition. So if I translate by a reciprocal lattice vector G, I get back to the same quantum state. Sorry. Yeah. I get back to the same quantum state up to a phase factor or a scalar factor. Actually, let's put it this way. I get back to the same quantum state, which means here it means a scalar factor, and here a unitary that does not depend on k. And this unitary here really has to do with the fact that the projective space is invariant under unitaries, and it has to do with Wigner's theorem. Okay. Here, these scalar factors, more precisely, these EGs of K's, are called the system of multipliers, and they are a system of multipliers which determine a line bundle over the Brillouin zone. And here, perhaps it would be nice if I wrote something in the board, but I don't know if the audience can see this. But the idea is that essentially this line bundle is determined as follows. So this system of multipliers must satisfy a condition that if I evaluate, so you see that these functions, these EG of K's, they depend on two variables. They depend on the momentum, and they also depend on the translation, the lattice vector. And so if I do two translations, E G1 plus G2 of K, then this should be the same as translating first with G1, and then after I reach K plus G1, I translate with G2. So they satisfy what is called the cycle property. Okay, so and in this sense, they determine an action of the lattice on a trivial bundle over R2. So if you consider the trivial line bundle over R2, then the reciprocal lattice acts on that trivial bundle simply by you take an element G, and it acts on a pair, a momentum, and a scalar in C by translating the momentum, and the scalar in C, it gets multiplied by the multiplier. And if you consider the set of equivalence classes, what you get is precisely the line bundle that I write there. UG is a unitary in the Hilbert space, so you cannot absorb it in the multiplier. But later we will see when we decompose H into irreducibles, then you will have multipliers which will carry that information on.
So here the multiplier takes value of the lines. It's a complex.
It doesn't take values in U1. It takes values in the invertible complex numbers. And this will be important because we will consider holomorphic wave functions in it.
So why UG is a matrix?
UG, you can see it as a matrix once you fix a basis in the Hilbert space. But UG has to be unitary. This is different. So while EG of K can be an arbitrary complex valued function, as long as it is not vanishing, the UGs, they have to be unitary because they must preserve the Fubini-Studi structure. Okay, this is important point. But we will get to that. Good question. So please.
So I suppose the momentum K sentence that kind of dual barrel.
So yeah. So this line bundle that I wrote there is a line bundle over R2 mod Z2, which is what you're saying. So I should identify this condition identifies momenta which differ by reciprocal lattice vectors, meaning you're on a T2. Yes.
Okay, that's fine. But I'm saying K from T.
Yes.
At this point, the K that I wrote here lives on the universal cover, so it is a representative of the K on the Brillouin zone. At this point, right. Here it's R2, but it projects to the quotient. Yeah. You're
And the line bundle.
It's a complex line bundle because EGs of K take values on C star. Sorry.
What's the dimension?
The line bundle, the dimension. Yeah. It's a one-dimensional. It's a complex line bundle. Yes. Okay. Let us continue.
Where is the second?
The cocycle condition appears once you do two translations, because this associativity here will imply the cocycle condition. Yeah.
So this would be
so there is a cocycle condition on the EG of K, which is also the reason why you have a line bundle. And then there's these UGs. They form an irreducible representation of the lattice. So this is the most simple cocycle condition. H2, yes. Very good. Good?
So for the, let's say in the two band case, UG is still an invariant matrix.
In the two-band case, it is a unitary.
So the EG will also be a matrix.
The EG, so since this is a line bundle, EG is a complex number. But if it was a vector bundle, it would be a matrix. You're right, an invertible matrix. A cocycle condition, yeah. You just have to be careful in the order you do the multiplication. But that's it. Yeah. Good. Otherwise, because you need you want to have a left action. Okay. Good. Shall we? So this line bundle, because of the construction, because it comes from a Bloch wave function, it comes with a natural Hermitian inner product, and it comes with a compatible connection. So the inner product is given by this. The Hermitian metric is given by this. Note the 1 over that. So essentially, I'm pulling back the anti-canonical bundle, the canonical bundle, if you want, the tautological. Sorry. And here A of K is the dual of the very connection. That's why there's a sign here. And the conventions are such that when I move to Kähler bands, holomorphicity will imply a positive Chern number. But otherwise, it will be. This is the convention. Okay, so compatibility just means that if I differentiate the log, this will be the log of the Hermitian metric. This will be the real part of the connection model. Okay. So because of that, L is an Hermitian line bundle.
Okay, remind what is the permutation?
It's this. So essentially, what this says is that if I have an equivalence class here. Oh, sorry. If you have an equivalence class of this, then you can define well, you know what is the square norm of this, and it's essentially this function h of k times modulus of v squared. Okay, that's that. Okay. And you can show, because the use of k transform with the EGs, that this will be invariant under gauge transformations. So this does not depend on the representative you choose for k. Okay, that's the important. You see, because v, if you choose a different representative for kv, the EG of k will pop out. But since this has 1 over it, it will cancel. Okay. You see, I mean, to be more explicit. So if you choose a different representative, means that you choose this, right? This is choosing a different representative, and then that would be h of k plus g modulus of v squared, modulus of the g of k squared. But since h of k plus g is 1 over the normal u of k plus g squared, this will be equal to h of k divided by eg of k squared, right? Modes of v squared, eg of k squared, and this will cancel. Okay, so this does not depend.
So, sometimes people use UK to represent a Bloch function, which is not nice. But so here is a completely different notation. The UK is not normalized.
It's not normalized.
So UK times D is Bloch.
Yes, yes. So UK being normalized means that you're using a unitary gauge. So here we're using an arbitrary. Very good.
So what is so you separate the right wave function as UK times D?
No. The Bloch wave function is just UK. But what I'm saying is that associated to UK, there's a line bundle, and this line bundle has an Hermitian inner product structure. That's just that. Fiber-wise Hermitian. Good. So
the wave function is not.
The wave function is not necessarily normal. It's good. So remember, UK plus G was equal to EG sub K UG times UK. Okay, and what I say is that these functions, this EG sub K, they satisfy this cocycle condition. Okay, and what I'm saying is that because they satisfy this condition, they determine a line bundle like this. Okay, and what I'm saying is that not only that, you have a line bundle together with an Hermitian pointwise metric, which is determined by the norm squared of U sub k. It's determined by this function. And a connection which is compatible with H, meaning that if you take sections and you take the covariant derivative, you take sections and you take the covariant derivative, this is equivalent. Take sections and you take the covariant derivative. This is equivalent to taking the exterior derivative of the norm. Okay? So it's just like the Levi-Civita connection. In the tangent bundle, this is the same compatibility condition, right? Okay, good. So, Hermitian, it just says that, so this is a line bundle over the Brillouin zone. And it said being Hermitian line bundle means that the fiber over a momentum has an inner product. And the inner product is this H of K. That's it. So H of K modulus of V squared is the norm squared of the equivalence class K, and that's why
Nothing's playing right now.
there's a gauge field. It's a U1 gauge field exactly because of this compatibility. It has values, so yes, you can. Well, I write it to have values in IR, but that's important. Yes, exactly. So the later on, the curvature of that connection will appear, and it has a Chern class. Yeah. There's no new information. I'm just restating things. Hermitian line bundle just says that you have that your transition functions can be made phases. That's it. And this is the usual setting in condensed matter, but it needn't to be. Okay? It's just a fact. Phases. So if you take a unitary gauge, which is if you divide, for example, by this, if you divide by this, then the EGs, the new EGs will be phases. That's transition function phases instead of complex scalars. Okay. So now I want to introduce a notion of equivalence of Bloch wave functions, and that is to say, if I have two families of vectors u sub k and u prime of k in the same Hilbert space, they are said to determine equivalent Bloch wave functions if there exists a smooth function here in the universal cover such that this condition holds. U prime of k is u of k times g sub k. Okay? So remark, if you do this transformation, then the multipliers e g sub k transform like this. And like in the example I gave below, so if you divide by the norm, this e g sub k become u1 phases. Right now, they are completely just invertible complex numbers, but I can make them e phases. And this transformation, in terms of the line bundle description, just produces isomorphic line bundles. Okay, so having two families that determine the same Bloch wave function means that the line bundles must be isomorphic. Okay, so in the simplest in our way of seeing things, they will have the same Chern number, they will have the same properties that we are used to. Okay. Perhaps a weaker and more general definition of equivalence would be two families u sub k and u sub k prime in the same given Hilbert space are said to determine equivalent Bloch wave functions if, besides g, there's also a constant unitary operator such that this holds. And this is natural. And it is related to the fact that the projective, the space of quantum states is the projective space equipped with the Fubini-Studi Kähler structure. Okay. Okay. Another remark is that if this happens, then the unitary operator U will be an intertwiner amongst the representations of the lattice, the UGs. Okay, so the U prime Gs are related to the UGs by this intertwining condition. Okay, good. Okay, now I move on to spatial structure of Bloch wave functions. So since the UGs determine a unitary representation of the lattice, then we can split it into irreps, right? And since the lattice is an abelian group, the irreps are one-dimensional, which are known as the characters of the lattice. So unitary irreps of the reciprocal lattice are basically labeled by points R in the real space unit cell. And these little r's. And the thing is that if I take R and I translate it by a real space lattice translation, the character stays the same. So essentially, there's a real space torus, which is the unit cell. And these points in the unit cell, in this real space torus, they label the reducible representations of the lattice. Okay, of the dual lattice. Okay, so using this, I will have the composition of my Hilbert space in terms of points in this real space torus. Okay, and in this H of R's, in this the unitary that I have before acts simply by multiplication by a scalar. Okay, and by the character. Okay, and this will give you the Bloch wave function condition. Okay. Remark: this direct sum is over a collection of points on the unit cell, and this collection can actually be, for example, in the case of Landau levels, the whole unit cell, and that's why and in Landau levels in the continuum, you have not UK just, but you have UK of R, and R is a point in a real space unit cell torus. Torus because if you translate by if you do translations, you go back to the same vector up to a phase, right? Okay. Exactly, precisely. I'm going to write that right now. So if you take the component UK of R in H of R, like G was saying, the UK, this condition that I wrote in terms of the UGs now is written like this: UK plus G of R is the same as UK of R up to the multiplier EG of K and this character. And now what you see is that you have a new multiplier, which is the old multiplier that you had for the line bundle, together with this character of the lattice. Okay? Okay, let us continue. And if you fix once and for all an orthonormal basis for HR, let's call it alpha of R, alpha from 1, 2, until whatever, and we write UKs of R in this way, what you find out is that the coefficients of this vector, they determine functions from R2 to C, which satisfy this condition. F of alpha R at K plus G is this new multiplier, okay, times F of alpha R of K. And what this means, this condition tells you that the alpha of alphas, they actually determine sections of a line bundle, which is determined, sorry, let me say it like this. They determine sections of a line bundle L sub R over the Brillouin zone, whose multipliers are EG of K and the character, product of the character. Okay? I will give a better meaning of this. So, and actually for each R occurring in this decomposition, we have one such line bundle. So you have essentially your model or your Bloch wave function gives you a collection of points in the unit cell, and for each point in the real space unit cell that appears, you have a line bundle. Okay? It follows from exactly from translation symmetry, right? So you're diagonalizing UG. Exactly. It's just that. It's just that. Exactly. And the UGs amongst themselves, they commute because the lattice is an abelian group. So you can simultaneously diagonalize them all, right? So let us go into the geometric interpretation of this. The positions in the unit cell, they determine these characters. And these characters, they define flatline bundles like this, which are basically using that construction there, where instead of the EG, you use the characters. And essentially, these characters, they twist the line bundle like this. So you have that line bundle, this mother line bundle that appeared before, and now you have these daughter line bundles, which are obtained from the original one, tensored with this flat line bundle. The UKs of R, they know of the spatial structure of the unit cell through the holonomy on these loops. What are these loops? Well, these loops are K of T equals to K plus T, translation by reciprocal vector. And the holonomy that you get is precisely the character. So let me make an illustration. So you have a point on the real space unit cell. The unit cell is identified with periodic boundary conditions, right? And then if you have one of these loops, which are non-contractible, once the wave function, once you go around this loop, the wave function receives a phase factor, which is precisely the character of the representation. Okay, so it's this e to pi ig dot r is the holonomy of a flat connection on this flat line. Okay. Okay, this is good. Now let us go on to quantum geometry in momentum space. So the assignment k goes to uk, determines a map, because note that this use of k is non-zero. Okay? Determines a map from the plane to the projective space simply by taking at each k the line on the Hilbert space generated by this use of k, right? And this uniquely determines Bloch wave function. The space, this projective space, is possibly infinite dimensional, Kähler manifold with respect to the Fubini-Studi Kähler structure. So here, P sub h is naturally a complex manifold, and you equip it with a Fubini-Studi symplectic form. And because being Kähler just means that the Fubini-Studi symplectic form determines a metric by simply putting the complex structure here in the middle of the sandwich. Okay. Besides, over this projective space, we have a natural holomorphic, Hermitian holomorphic line bundle, whose fiber over a line is the line itself. This is known as the tautological bundle. Okay. And the Fubini-Studi symplectic form is simply the Chern connection for this Hermitian line bundle up to factors of pi. Okay, the curvature of the Chern connection. So P sub h is the projective space of the Hilbert space. So it is as a set is the set of one-dimensional subspaces of the Hilbert space. It is a manifold. It is a complex manifold, and besides being complex, it's also Kähler with respect to this symplectic form. Okay. How do you prove that this is compatible? So you can show. So you locally. So first of all, this has a complex structure which is given. I mean, in the finite dimensional case, it corresponds to taking ratios of the coordinates, as long as the coordinate in the denominator is non-vanishing. So this gives you a holomorphic structure. And then the Kähler structure is given locally by del bar of the Kähler potential, which is simply the logarithm of the norm squared. Okay. So this you can show, and then you can see that it patches together. Exactly. So for an n-band system, pH is CPN minus 1, right? Good. Okay, so definition, Berry curvature and quantum metric. So the Berry curvature F and the quantum metric G of the Bloch wave function use of K, they are respectively the pullback of 2i times Fubini-Studi symplectic form and the pullback of the Fubini-Studi metric. And this F here, since this was the curvature of a connection on a line bundle over projective space, by naturality, this is also the curvature of a connection on the Brillouin zone. And it is precisely the connection that I wrote there to start with on now. Okay. Proposition, quantum geometry in the Brillouin zone, because before, when I wrote these pullbacks, remember that F is a map from the plane to projective space. So it doesn't mean that this F and this G go down to the Brillouin zone. It could be that they were not periodic, but indeed they are periodic. And this you can show. So this is the first part of this proposition. And then not only that, the tensors f and g, they actually depend only on the Bloch wave function and not the particular representative. Remember that I introduced an equivalence relation between Bloch wave functions. And what this says is that this only depends on the equivalence class, okay? Well, the proof is actually a few lines. So because of this condition, this was the definition, right? Then consider this diffeomorphism, which is what you quotient, right? Then we essentially have that the composition of the map F with this translation is intertwined by this U of G. But note that when I take the quotient to the projective space, this is just the face, so it doesn't appear on the right-hand side. Your F is simply this. Your F is essentially the map induced by this. So if you want in terms of projectors, your F is this. If you see the Fubini study, if you see the projective space as a set of orthogonal projectors of rank 1, this is the map F. Okay. Another thing is that the Fubini study symplectic form and the Fubini study metric, they are invariant under unitaries. And because they are invariant under unitaries, F and G are so. Okay, that's it, because of this intertwining form. The second part also follows from equivalence of representatives being done through automorphisms of, well, automorphisms of the projective space, projectivization of the Hilbert space together with the Fubini to the symplectic form, they are simply unitaries. Okay, there's nothing more. Okay, so now we move on to Kähler bands. This is the main subject. So a Kähler band is determined by a Bloch wave function U sub k, such that this map is holomorphic, and not only that, is a holomorphic immersion. That means that the derivative of this map is injected, okay? With respect to a complex structure J on R2 that is invariant under reciprocal lattice translations. And why do you want that? Because you want this complex structure to go down to the Brillouin zone. That's what you want. Essentially, if you write this in kx and ky coordinates, that means that the matrix J, which is a matrix which squares to -1, it gives multiplication by I on the tangent spaces, has to be a periodic matrix. Okay, that's all it means. Okay. So for a Kähler band, these, the pullback of the Fubini to the symplectic form, the pullback of the Fubini to the metric, meaning the quantum metric, and the complex structure J, they determine a Kähler structure in the Brillouin zone. And that's why we call them Kähler bands. Okay, that's the reason. And now let's go to the concept of ideal Kähler bands or ideal flat bands. Okay. A solid state pointer. That's good. So in ideal Kähler bands, also known as ideal flat bands, these are special Kähler bands which are where the complex structure is not only translation invariant under dual lattice translations, but also translation invariant. Actually, there is a uniformization theorem in the theory of Riemann surfaces, which states that basically I can, using a diffeomorphism of the Brillouin zone itself, I can always bring the complex structure to this. So actually, this ideal Kähler bands is the most general setting up to diffeomorphisms. But diffeomorphisms are nonlinear. So you know that such diffeomorphism exists, but to build it, you can do it abstractly, right?
Uniformization theorem is valid for any theorem for the all dimensions.
No, uniformization theorem is a theorem for Riemann surfaces. And what this says for our particular case is that if you have a Riemann surface of genus 1, then it is bi-holomorphic, meaning isomorphic in the complex manifold category, to the Brillouin zone equipped with one of these complex surfaces, translation invariant. Good. So this is actually pretty general. Okay. And so these translation invariant complex structures, they are determined by a modular parameter which lives in the upper half space. Okay. And you can basically describe it in terms of a complex coordinate which is of this form: kx plus tau ky, where tau is in the upper half space. Good. So now we move on to the structure theory of ideal Kähler bands. So an ideal Kähler band will satisfy this condition in an arbitrary gauge. What this says is that the mapping that I told you is holomorphic. Okay, the mapping to the projective space is holomorphic. And actually, you can choose by multiplying this use of k by a g sub k. We remember we had this degree of freedom. Then we can bring this to this more simple. And this happens specifically in 2 dimensions. You can do this. Okay. We can then assume that the E gammas, the multipliers, the EGs, they will be essentially holomorphic in this complex variable. And what this means is that the line bundle L, and in fact, all of the other line bundles, the daughter line bundles, also are, they are holomorphic line bundles. Okay? Hermitian holomorphic line bundles. It's actually a very good setting, and it's closely related to that of geometric quantization in a Kähler polarization. So let us continue. So now, what we're going to go to is essentially theta functions. I mean, whenever you see line bundles over holomorphic line bundles over tori, you expect theta functions. So what I'm saying here is that a holomorphic line bundles over complex tori, they are always isomorphic to holomorphic line bundles whose sections, holomorphic sections, are described by suitable theta functions. Recall, so this is the theta functions with characteristics A and B. This is given by this convergent series expansion, and the characteristics A and B, they appear here. And so this statement of isomorphism of line bundles just means that I can, by multiplying by an appropriate use of k, then I can bring this multiplier to this canonical form. Okay, and this is the multipliers that appear in the quasi-periodicity condition of this function. Okay. So this this C that appears here is very important because it's actually the Chern number of the line bundle L sub R, and it's by Riemann-Roch. It's the dimension of the space of sections of these holomorphic sections of this line bundle. Okay. So you see that the Chern number is counting how many states we have in this space. Okay.
The same degree of the R is physically fix the coordinate R and compute dividing of the
Exactly.
This is the same as in real space integration and
Yes. And so remember that I told you once you expand your use of k of R in a basis, then we had sections, right? The coefficients of expansion were sections. But now the sections have to be holomorphic. And that means that they have to be linear combinations of these guys, okay? And so what that means is that each of these coefficients of UK of R, they are constrained to assume this form, okay? They are written in terms of theta functions, and for each R, you have C of them.
This statement is that an absolute statement proved by
It is proved. I can give you a reference. This is you can find, for example, in Manfred, taught lectures on theta, for example. Yes. Or there's actually a review article by Overview. This is also good. Yeah. Right. There is some sort of thing that you can do. Well, maybe it's better to discuss this later, but there are things that you can do. Yes. Okay. So structure theory of ideal Kähler bands. So for an ideal Kähler band with a complex structure determined by tau and Chern number math call C, then we have this expansion for each R, and this is what we conclude, right? These coefficients, they are expandable in terms of theta. If the Chern number is 0, this is not interesting because it's not an immersion, right?
So the Kähler bands doesn't apply to the Chern number.
Well, that is the most trivial holomorphic map, but then it's not a Kähler band because the pullback of the metric will
Kähler band
excludes C equal to 0. Yes. I mean, if you want to put C equal to 0, I guess you can, but there's no interest because there's only one section of the trivial holomorphic line bundle, which is the constant function, right? Because so it's not very interesting. You would end up with a constant. Okay, but that's an interesting question. So let's one important thing is that these coefficients, they actually depend on a few things. They depend on the particular idea of Kähler band, and they also depend on the choice that you made for these spaces. Okay, remember that I had to pick a basis to write this. Okay, and this will give us a gauge degree. Okay. It's a real space. It's a choice in real space. Yes. 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 So you choose a point in the unit cell, and the local Hilbert space. You are choosing a basis for the local Hilbert space.
They find out that the complementary geometric geometry is
invariant.
Not invariant.
It's not invariant. Right.
That is minimum of the value of the
Yes. I am familiar. I am familiar with this. That's true, and that has to do, if I'm not mistaken, it has to do with these UGs. Okay, and that's important. Very good point. Well, very good point. So now we move on to the main point, which is more special case. Definition: flat Kähler bands. A flat Kähler band are Kähler bands for which the quantum geometry is translation independent. And that means that if you use the kx, ky coordinates, the tensors g and f are constant. Okay, that's what it means. Consequences. For every translation q in R2, we have a diffeomorphism of the Brillouin zone, given like this, taken mod Z2. And translation of the invariance of the quantum geometry means that these pullbacks preserve the geometry, right? And now, this fact here, that G is equal to F star, the fact that this is invariant under phi q means that phi q can be associated with an holomorphic isometry of the Fubini-Study metric in the target space, target projected space, which then leads to the Hilbert space to act as a unitary operator. If you want this is some kind of magnetic translation. That's the way I've seen. And this is related to Wigner's theorem. So quantum symmetries, they are isometries of the Fubini-Study metric, and they are represented by unitary or anti-unitary operators in the Hilbert space. But this is morally. The way you prove this is essentially a consequence of the rigidity theorem of Calabi.
When you say the isometries of Fubini-Study metric, would that Fubini-Study you mean the Fubini-Study in the CPN?
Yes. So what you can show is that if you have a diffeomorphism of CPN that preserves transition amplitudes, okay? Transition amplitudes only depend on the states, right? Not on the vectors. This is equivalent to an isometry of the Fubini-Study metric. Okay? So the only maps are such, and then you can prove that through differential geometry that the isometries of the Fubini-Study metric are projective unitary or anti-unitary operators.
So I can understand the symmetry as a symmetry operating in the single space. That's CPN.
Yeah. So this symmetry, yes.
So
I just say that it's a quantum symmetry because it's a symmetry of this object. But no, sorry. And since an anti-unitary operator would change the sign of the Berry curvature, this you can see because the Berry curvature depends on the wedge product, and complex conjugation flips the wedge, then this use of Q must be unitary. Okay. And now what you look is that these lifted unitaries, they will form, because they will have to close up to a phase, they will form a projective unitary representation of the translation group. And what that means is that you act with two translations and you get back the translation of the sum, but up to a phase, right?
this UK
This UK is essentially the lift of this phi q, which will give you a quantum symmetry. Okay? It's the magnetic translation. This will be a kind of a magnetic translation, but okay. Projective unitary representations of the translation group form unitary representations of central extensions of the translation group by U1, which go into this short exact sequence of groups. So here U1 is injected in this group, and if you lose the information once you just focus on translations. As a set, this group here is given by the Cartesian product, but we have a twisted product law where you the decays you sum, but the phases you make the product using the co-cycle. Okay, and now you can show that central extensions of the plane by U1 are determined up to isomorphism of central extensions by the commutator, which is this ratio, which you flip the K1 and K2, and you can show by the properties of the co-cycle condition that this has to be of this form, where omega of K1 and K2 is an antisymmetric bilinear form. What that means is that it can be represented like this, where D is a constant, and this is the standard skew-symmetric form in R2, right? When D is 0, what you get is the trivial extension, meaning the product is just the group, the Heisenberg, the group is just the product, the direct product. But if D is different from 0, then what you get is what is called the Heisenberg. Once a concrete realization of this co-cycle for a given S is given, you have a group, and all other realizations differ by an exact cochain. It means that where this is a function to the circle, and what this means is that this is an isomorphism of central extensions. A concrete realization is provided by you take this side and you write like this, and you can show that the commutator gives you precisely this omega that I wrote. The title? K1, K2 is a title. Yes. Thank you. You're very attentive. That's good. Okay, this is what I was saying, that when D is equal to 0, this is 1, so there's the product structure is stable. And now there's a very important theorem, which is the Stone-von Neumann theorem, which states that the Heisenberg groups G, the Heisenberg group G, has a unique, up to isomorphism, unitary irreducible representation, where the Hilbert space is precisely the square integral functions of R, the space of square integral functions of R. So a particle on the line. This is consistent with the idea that we have that when we go to the lowest Landau level, we effectively just have one degree of freedom. We don't have two, right? And for which U1 acts in this standard way, and the action of this element is given by multiplication by lambda and this translation here. And this is the standard Hilbert space of a particle moving in dimension 1 with a coordinate, abstract coordinate q, and for which the momentum is given by 1 over id derivative with respect to. And note that d is constant. D is like a Planck's constant, okay? Effective Planck's constant. You will see that it is related to the Chern. Okay, let us continue. So from this theorem, then we can build a translation invariant Bloch wave function by acting like this. You take UK and you act with a constant, on a constant factor. But note that we have a Kähler band, and that means that we have a holomorphicity constraint. So to deal with that, we use the Baker-Campbell-Hausdorff formula to split this in this form in terms of creation annihilation, bosonic creation annihilation operators. And now holomorphicity will mean that this function here, the UK, cannot depend on Z bar, so it means that this A of tau must annihilate the vacuum. No, sorry, must annihilate U0, which means that U0 is the vacuum for this bosonic oscillator. Okay, so we continue, and this is what I was saying. But if you go explicitly, you show that U0 of Q has this particular form. But now remember that this has to be a square integrable function, and that imposes constraints on B, right? One of them is that B must be smaller than 0, because otherwise this would not be square integrable, because tau is in the upper half space, which means it has positive imaginary part, which means that D must be negative. Okay. The other thing that I said that U0 is the vacuum of the bosonic mode. And actually, we know these states. They are bosonic coherent states. Okay. They are coherent states associated to this bosonic modes. And now we have further constraints because UK determines a line bundle. This is the initial of my story, the beginning of the story. We had a line bundle, remember? And then, because of that line bundle, you just remember that you know, this state was defined using the UKs. You do this translation. You see that this translation satisfies this twisted product rule with a cocycle. And then what you see, using the definition of Bloch wave function, you can identify this EG. And you see that EG of K is simply related to this cocycle evaluated at these 2 points. One of them is a reciprocal lattice translation, and the other is the moment. And then what you can see is that for this to determine a line bundle of the Brillouin zone, D has to satisfy certain constraints. And now, using this multiplier, we can determine a connection on this line bundle by noting that a connection will be given by a one form on the universal cover, such that AK plus G is equal to AK minus the derivative of the logarithm of that. This is just saying that under gauge transformations, the gauge potential must transform in the property by a derivative, right? Very good. And if you do that, an example of such connection is this. You can see that this transforms in the way, and the curvature is given by the exterior derivative. And because you know that the curvature of this integrates in the Brillouin zone to a Chern number, you find that D must be this quantity. Okay, so you found an action of the Heisenberg group, the Heisenberg group, and the Heisenberg group will have this D determined like this. Planck's effective Planck's constant determined by the Chern. Okay. Now, if you want the real form of UK of R, because up until now I didn't give you wave functions, I just told you that they exist. And they are unique up to the extent that the Stone-von Neumann theorem states that irreducible representations are unique up to unitary isomorphs. And now, what I can do is use the Bloch transform in L2 of R to build the irreducible component that transforms with the irreducible representation R. This is done by simply summing over the action of the translation, weighted by the appropriate character. And what you can show is that this F of R transforms in the good way, meaning that if I take under translations, this receives the appropriate phase factor. Okay? Okay, so what you can show is that this F of R, it actually determines a square integrable section of a Hilbert bundle, not now over the unit cell torus. We denote this Hilbert bundle like this, H over. This is not the Hilbert space, this is a Hilbert bundle. It's a bad notation. But essentially, the fiber over R is really this space here, H of R. And this space is spanned by, it's not a coincidence, by math-cal C, Chern number, independent distributions. And this, which says that this H of R is actually isomorphic to the space of sections L of R. Okay? So if you actually do this computation, what you find in the basis determined by these distributions is that UK of R is just the theta functions like this. So you remember that for a flat Kähler, for an ideal Kähler band, you would have arbitrary linear combinations. here you have specific linear combinations. You cannot have all of them. But there is still a gauge degree of freedom, which I will specify later. But for c equals to 1, you can show that this wave function is precisely the lowest Landau level wave function. Okay? Bloch wave function. And for c greater than 1, this determines the so-called polar entangled Landau level type wave.
Yeah, this wave function is c component
Mm-hmm.
wave function.
Yes.
The current
Yeah. So you
this is just
okay.
so current wave function describe the wave function of number c larger than 1 band. So it's still
But this is right. But this is c larger than 1. So this is
current is still described that line bundle, but that's number 9. Here
it's still line bundle, and it has it's a line bundle.
It's a transfer function is a base, right? So in this sense, you're call it.
Yeah.
But I think I have to spatially sum all pieces.
Okay. We can discuss this later. But in any case, this is unique. And actually, this is related in mathematics. So it actually has a very nice property, which for each R, this is actually the Kodaira embedding associated to the line bundle L R. So this has because these functions, they form a basis, an orthonormal basis of the space of theta function. So it's actually a very special geometric object. Okay. So besides this, there are gauge transformations. So the Stone-von Neumann theorem states that this unirep is unique up to isomorphism. And what that means is that you can basically these unitary operators, they are determined up to a constant unitary. And because the isomorphism will preserve the quantum number R, then this means that locally there will be use of C, where U is the unitary group, gauge transformations. So this vector wave function that I wrote is defined up to use of C gauge transformations. And besides that, we are also able to perform momentum space C star transformations, which were the initial ones I did. So I reached the end of my talk, and the summary is: you fix a flat complex structure in the Brillouin zone, which is parameterized by tau in the upper half space. You fix a Chern number greater than 0, and then flat Kähler bands are unique up to this gauge transformation. So this is the end of my talk. Thank you.
So I guess I should see the participants in case they ask questions, right?
Is there any questions from audience? And audience on YouTube?
There's online people. But they are quite silent. Either I am silent. No, there's no one speaking. So
Please.
How much of this orem and the generalized vector bundles, and how much of the
So there is one straightforward generalization, which is so you can go to higher dimensions following this construction, and you still have Stone-von Neumann theorem. But what you essentially end up
is from T2 to T4.
Yes, for example.
Stay at T2 but consider that.
Okay, if you stay on T2 and you consider vector bundles, then I don't think you have uniqueness. So, and the reason is that essentially the theorem that helps with this construction is a theorem of Calabi, which states that essentially if I have a Kähler immersion, meaning a holomorphic immersion to projective space, then this is uniquely determined by the Kähler metric, by the metric, up to unitary. If you have a vector bundle, then you don't have a map to projective space, but you have a map to the Grassmannian. Okay? And in that case, there is no analogous result, I think.
Can you explain why for vector bundle line? That is it, but that seems a very important difference.
It is a very important difference, yes. So you're asking why it doesn't hold, the uniqueness result doesn't hold. I cannot explain you immediately. I did go through the proof of Calabi's rigidity theorem, but for the case that the Brillouin zone is two-dimensional. And this is a result, this can be found in a paper by Griffiths, the same Griffiths, or yes, I think it's Griffiths or Harris from the algebraic geometry guys, and this is based on moving frames, and the proof follows from using the fact that if you have so if you have two maps, from a manifold to a unitary group, such that the Moret-Cartan one form is the same, the pullback of Moret-Cartan is the same, then they differ by a rigid unitary. This is one way of proving it. I don't know exactly how the proof fails, because what the proof relies on is the existence of moving frames. But we can discuss this later. But I know the proof doesn't hold because I've looked into math papers and people show that the metric, the Kähler metric, does not determine uniquely the map. So this is a very special thing that occurs in the non-degenerate case, in the line bundle case. Yeah. To 4 dimensions, exactly, you have two possible generalizations. Either you have an abelian gauge field, and then it's just this construction, tensor product of this construction. Yeah. Mm-hmm. Vector bundle is the same problem. You'll have the same problem. Yeah. But it's, I guess, that makes it even more interesting, habits. So, because there are some results in that direction, but it's specific. It's specific to dimensions.
For the 4th dimension, in a 2D, the local complexity implies the global complexity, but in 4D, you have to satisfy integrability.
That's right. That's right. The complex structure will not be given. So you're talking about these inequalities, the saturation of inequality. In that case, you have to define
once you have this global classifications, then the classification should be in 4D like.
I'm not completely sure. Not completely sure. I don't want to say yes because I'm not sure.
Sorry, I got locked out.
Oh, hi.
We met over Zoom meetings.
Ah, I remember you. That's true. Did you have long hair back then? That's right.
While I was waiting, I skimmed your papers. So I think
okay, that was quick. Great.
I skimmed it before, so I reskimmed it.
You reskimmed it. Mm-hmm.
I guess you just finished.
Yes, I just finished. Feel free to ask questions.
Oh, actually, your question. So there was this. So I understood as far as it went, the boundary conditions, but then At one point you said that there's a, at least in the paper, I don't know if you want to talk, but you said that the flatness of the Fubini-Studio metric implied that there were a set of operators UK that were in all the Bloch states.
The proof of that is not in the arXiv paper because we were replying to referees and then we proved that in detail. But the way to do it is basically follows from Calabi rigidity. So you can, it's a consequence of this. So if you have a map from manifold to TPM, which is holomorphic, so the M is holomorphic and this is holomorphic, and so you have two such maps, such that the Kähler metric is the same.
So I should think of F and F prime as like UK.
Exactly. So
let's say F is like the
exactly. So this F, in fact, let's put M to be the Brillouin zone or R2. Let's put this. Let's think of it this way. And suppose that F and F prime give you the same quantum metric. Okay? Then it means that F and F prime necessarily differ by a unitary operator. Okay, this is a Calabi rigidity.
A unitary operator that that's a function on the Brillouin zone, or
no. So this U is you can see as
so U is an element of CP.
Exactly. So
and
in
fixed.
yes, and in particular, what you want to apply, you want to choose F to be determined by use of K. You want to choose F prime. So let's put R2 here in the universal term, because this is actually the universal. So you want to choose F prime to be UK plus Q. And what you show is that these are the same. Therefore, there exists a U which depends on the translation data. And this is how you show. This is how you show. Yeah, unfortunately, when we first wrote that, we didn't take that detail very deeply. But once we digged into it, this popped up.
I see. So that gives, okay, so it's Calabi rigidity.
Okay. It's holomorphicity, basically. Holomorphicity is so holomorphicity and the fact that your band is non-degenerate. Because as G was asking before, in the vector bundle case, when this is the Grassmannian, yes, then this does not hold.
Yeah, that makes sense.
It's a bit more, so this whole thing goes into central extensions of the translation group. I would expect that there you do not have a central extension, but you have something more complicated. You have a group extension, but it's no longer an abelian extension, I think.
Yeah, you get these like Jordan blocks.
Something like this, yeah.
We can talk more about that, but
I would love to.
yeah, me and Dan Parker have been on the case.
Okay.
Not for flat, but for like we didn't show uniqueness for flat, but it's a different thing. We can talk more about it.
That's very interesting. Great. Well,
thank you. That makes a lot of sense.
Thank you. Thank you for that question. It was very, very good. Thank you very much.